Good evening, gentlemen. Welcome to the seventh episode of the Nodutalk. In this topic, we are going to cover mechanism of inoculation, why inoculation should be done, which are the materials available for inoculation, how much should be the addition, how to decide the addition of the inoculation, efficiency means recovery or effectiveness of the inoculation, what is the incorrect addition, and what are the results due to incorrect addition and not getting the required result. Influences of various elements which are present in the inoculant means how to select the inoculant and method of inoculation. So you might have noticed that method of inoculation is last because we all are practicing foundrymen, so we know how inoculant is added to the metal. So that we are skipping the theory part of most of it, and we are covering the practical tips amongst this. And with his vast experience, Mr. Hendricks can solve or guide your query about your queries regarding inoculation or any other foundry topic. So I now hand over to Mr. Staff Hendricks for today's presentation.
Good evening, everyone. Let's go through the whole presentation, and if there are questions at the end, we can always try to answer them. So, why do we inoculate? It's good that we remember it and we realize it. It's to assure that we have the proper number of graphite segregation in the correct shape of nodules. And the graphite segregation is initiated by nuclei, as we know, but which are small particles smaller than 10 micrometer, containing oxides like silicon oxide and cerium oxide, and sulfides, mostly magnesium sulfide and cerium sulfide. That's one of the things you have to realize. You need both to have good nodules. But there are still a lot and several theories about how the free graphite is formed. We are not going to detail all this because it's a matter we can have months of discussion about all this. So, basic, we have to control the number and type of nuclei at the time of solidification, because we know that the nuclei will be the start of nodule. And extra, we have to be aware that we have to control the nuclei fading, which is time related, because we can control at moment one, but the solidification is maybe 5 minutes later. So the fading of the nuclei is also very important. So the inoculation is performed by adding alloys containing silicon. Why? We know that by the nodulizing we have sulfides. We have magnesium sulfide, we have cerium sulfide, but the silicon is not sufficient anymore, and we need silicon for making nuclei as silicon oxides. Some other elements are also present, but in a smaller amount. That's cerium, bismuth, barium, zirconium, and sometimes very small amounts of sulfur and oxygen even. The types of ferrosilicon containing some extra elements, the cerium we mostly use for having the good nuclei in thin section casting. Bismuth is the same, increasing the number of nuclei in thin section cast. Barium is better suited for medium and thick section cast. Why? We will see it later. Barium components have a higher density and will less float. That means have less fading. One thing in the bottom, you must be aware that inoculant for thin section castings will be different from the one of thick section castings. So if you make thin castings and thick castings, don't think you can do it with one inoculant. You will have to realize that you need more types. Here we see some of the potential inoculants by Castwell, and you see the silicon is all around 60 to 75%. You have three types with barium. Remember, that's for medium and thin sections. You have the ones with manganese. I am not using that much in ductile iron because manganese is not the best element for adding it more in ductile iron. But it can be. It anyhow decrease the solubility, let's say the melting point of your inoculant. You have the ones with calcium, and there we have a whole range, because the calcium is an element that can help magnesium for, let's say, binding the sulfur, and later on it can help that the magnesium is not fading very much away. I am not in favor for higher than 3%. Even 3% of calcium, you should pay attention. It's why it makes a liquid slag. And as you know, liquid slag cannot be held by a filter in the pouring system. So it goes inside your casting, and then it can cause trouble. Aluminium, you have from 0.5%, nearly nothing, till 2%, even there. Aluminium is adding, but pay attention, for you can risk pinholes, especially let's say in the monsoon season, when everything is high humidity. Aluminium is a little bit dangerous. Zirconium is an element that can be used for mainly thin castings, but be aware that zirconium will react also with aluminium. So there will be an interaction between zirconium and aluminium. You have strontium there in the bottom, you have bismuth, and then the TRE is total rare earths, 3 to 3.5%, only for thin casting such high percent. So how much do we have to add? We must realize that we do it mainly in two parts, the inoculation. There is a third part, we come better on it, that's the conditioning, but we will talk later on. First part is in the ladle, the second part is in the late inoculation of the stream inoculation. The first inoculation is performed shortly before or even together with the nodulizing. This is the basic inoculation. You know, you have foundries who do it during the tapping on the nodulizer, that they also add already inoculant. You have foundries who have in the bottom of the treatment ladle, they put the nodulizer plus some inoculant, and then the covering by some thin steel sheets. That's this. The late or stream inoculation is performed during the pouring, and that's also very effective, because it's the last time you can change, and you change something on the metal. Why is that late inoculation effective? Because during the pouring, the metal is in contact with the air, and you will have absorption of oxygen during the pouring. And this oxygen can very easily make SiO2 nuclei, which is needed for making the nodule. Pay attention here. Important factor is the size of the inoculant. How much do we have? There is no formula for calculation. Be aware of that. No one can give you a formula of calculation. It depends on the basic metallurgical quality of the liquid metal before and after nodulizing. And that will many times be different. So be aware, a calculation will not help. What can we use? We can use the cooling curve of the thermal analysis equipment. That's the best tool in the foundry itself for deciding how much inoculant you will have to use. It depends also on the time of inoculation compared to the time of pouring, or better to the time of solidifying. So you can take a formula for calculate your inoculant, but if you wait then 5 minutes between the inoculation and the pouring, or you wait 2 minutes, the result will be totally different. Be aware that indeed it's the first inoculation and the last inoculation compared to the solidifying, because there is still a lot of contact with the air and turbulence during the pouring and mold cavity filling. And this will affect the whole metallurgical situation of your metal. We come later on that. How do you do it then? It's based on experience and your process consistency of melting, nodulizing, and inoculation. Why is that? If you melt the metal, we have seen it in the two previous presentations, and you are a long time on temperature, or you are short on temperature, you are on high temperature or not on high temperature, the condition of your metal is totally different, and the condition of your metal decides at the end how much inoculant you need. need? It's mainly the presence of oxygen. Why? We need to make silicon oxide. And if you have too long on high temperature above the TC temperature, as we have seen before, then your oxygen is out of your metal and you will have big problems to get the correct number of nuclei. It's also different due to the nodulizing, because as we said, we need silicon oxide, but we need also magnesium sulfur mainly. And the magnesium sulfur is sized or small sized. You have a lot or you have not. It's different from each time you do it again and again. As we said, we should talk about the active magnesium content, as we have seen before. It's the magnesium content from your spectrometer minus 0.75 the sulfur content. And that's the active magnesium who is ready for doing extra, let's say, binding of sulfur or whatever. The cooling curve. Every one of us know or should know the cooling curve. This is the cooling curve with the cup who has no tellurium. Why? If you have with tellurium, you don't have the cooling as it is in your mold. You should have without tellurium. And you can see there are a few very important things on that. You have what's called there TE gris and TE blanc. That's the top, let's say, that you have the good solidification. Below the TE blanc, you will have more carbide. In between, we have delta T. That's the lowest point of your cooling curve compared to the TE gris. And you have the R, and that's the reculency. On next slide, I will tell you. It's between the lowest and the highest point that indicates a tendency of initiating free graphite. The larger the difference is, the lesser active nuclei, and consequently the lower the amount of nodules. In the end, if the cooling is steep, then we will have free graphite until the end of the solidification. Can we go now back to the graph again? You can see, how is it possible that we let cool a metal and all at once its temperature increase again? How is this possible? Normally the temperature should go down continuously. No, it increase again. How does it be? If we have dissolved carbon in metal, we have put energy to dissolve it. Now, when the carbon is coming out, nature is fair, it gives the energy back. And by giving the energy back, the temperature increase again. So what does it mean if we look at the curve? The moment we are still cooling, that means no graphite is coming out. And when the graphite is coming out, the temperature goes up, and R, the reculency, is a little bit, let's say, a measure quantity to see how much is coming out. At the end, what do we see again? If the curve is going down like it is in this graph, very, very slowly down, that means that there is nearly no graphite coming out anymore. It's just cooling. And we should like that the graphite is coming out until the solidification. Because if it doesn't, then at the end, we have microshrinkage. So what should we do? We should have a curve with a low, let's say, R, that the graph is not going much deeper than, let's say, and not cooling down and coming up anymore. And at the end, we should have a graph who stays very high, the line stays very high, and then all at once drop down. If it all at once drops down very steep, then we know the graphite was coming out until the last minute, and the chance or the risk on microshrinkage is very, very low. Please work with this cooling curve. It's really very, very important for deciding about your inoculation. We have seen this, so yeah. Now for the oxide. The efficiency of our inoculation is mainly depending on the oxides, because we know that if we do the nodulizing, our oxygen is going out by forming magnesium oxide, and we have no oxides anymore for making the good SiO2 formation. The graph you have seen there is, we have seen it before. If you go left of one of the lines, you see that the silicon oxide is split in silicon and oxygen, and even carbon plus oxygen is leaving as CO. So this is a very dangerous area because there we lose oxygen a lot. If we go under the lines, then we see silicon plus oxygen is making silicon oxide. So that's the area where we make nuclei. And this is a graph for saying a little bit. You see the base iron. Why is there another one? Why in the base iron there is much lesser silicon in the furnace. You have the ductile iron final, you have the CMO and gray iron. Everything is done there. Mainly remember that we need oxygen for making silicon oxide. And magnesium reacts also with sulfur if there is less magnesium oxide formation. So please never take all the oxygen out of your metal before you do the nodulizing and before you do the inoculation. Again, the formula, we have seen it before. The TG temperature, that's the temperature, let's say, where we form silicon oxides. It's given over there with the formula. And the TC temperature is also given in function of the TG temperature, and that's the one above that we lose oxygen. So the TC and TG are depending on the silicon and the carbon who is already in your liquid metal. Each melting has a little bit different temperature, and we really have to realize that we have to do a consistent melting, same temperature, same timing to make sure that we have a good and the same metal for doing the nodulizing and the inoculation. If we stay longer on high temperature, we have a different result. If we stay not on high temperature, we will have a different result. Please realize that. We said we need silicon oxide and we need sulfides. The sulfides are magnesium sulfur, cerium sulfur, and lanthanum sulfur. They are required together with the oxides to form the good nuclei and who will let that the segregation of correct nodular free graphite will be there. Inoculation can also form extra sulfides if the correct elements are present in the inoculation. That's barium, for example. I come later on that. I can tell you now, some sulfides are stronger in the formation than others. So they can even, let's say, destroy certain and form their own sulfides. But we come later on this. The time and the type of inoculation of the low temperature. I know that foundry men are always afraid of the temperature. You know why? That's due to the manager and the owner. If the temperature is too low, it can be that the casting has cold run. And everyone knows then if there is cold run, the guys in the furnace and doing the treatment have done a mistake, so they are blamed. If you see what the effect is, if you do an inoculation at different temperatures, it's just one of the tests I did, same furnace, and we did the inoculation at different temperatures, and you can see at 1325, which is a low temperature, I am sure, and only available for large castings, you have a nodule count of 120 in that test. Says nothing for the rest. But that goes down. If you go at 1400 degrees C for the inoculation, it's only half. And if you go at 1500, yeah, it's nearly nothing. Now, no one will inoculate at 1500. I agree with that. But it's a matter of showing you that please pay attention. The temperature is very, very important. That graph here at the right side, you should always keep in your mind. Why? Because of the fading effect that we will have for each inoculation, even nodulizing, but also the inoculation is there. What is fading? Fading comes partly because later the oxides and the sulfides will float up. Due to the speed of floating up in the ladle depends on their density. And all these, let's say, oxides and sulfides, who are at the right side of this graph, have different densities. So some of them are very, very good. Some others will disappear very, very quickly. And it's, of course, necessary that we see which one we will have. The highest of, let's say, the lowest minus, the higher in the graph it is, the quicker it will be formed. So you will see that mainly you will form calcium oxides, cerium oxides. Magnesium oxide is also fairly high, but also barium oxide is fairly high. Silicon oxide is very low. That means that silicon oxide, even if it's there and you do, let's say, you add some of the other elements who are above, it can be that the silicon oxide is destroyed and make another oxide. For the sulfides, it's the same. You can see that in the bottom you have magnesium sulfur, but above lanthanum, calcium, cerium, barium, they are much more stable and they will be formed previously. So that if they are present, they are really playing a very important role, and not only the magnesium sulfide. What is now the third thing we said here already? Preconditioning is an alloy containing elements that form nuclei before the nodulizing. So that means mostly in the furnace, and if you add there barium, it will be formed. It will take already oxides. Barium oxide will be formed before the silicon oxide is there, before the magnesium oxide is there. And barium oxide will not be decomposed by the others because it's there from in the furnace. So barium is a very, very important element in thick and medium-sized castings. The sulfides is the same. If you put barium already in the furnace, it will make already partly barium sulfides. And you will need less magnesium for, let's say, binding the sulfur to make a good ductile iron. Very important, and we come back on this later. The free energy, as I said, is, let's say, an indication how quick it is formed and which one will be formed before first. Barium is very, very important if you have medium and thick sized castings. There is another one, and it's not in the graph, but I know it during my whole career in the foundry, and I have been taught it by an old foundry man in 1970. Silicon carbide, it's very, very cheap, and the foundries now, they have forgotten it. But what does it do? When you use it as a preconditioning, silicon carbide splits very, very slowly. So it takes quite some time before the silicon carbide delivers silicon to the metal and carbon to the metal. And it's a very important element for preconditioning. Incorrect addition. An incorrect addition can be due incorrect calculation, and it's a wrong word, calculation. Before I said to you, you cannot calculate it. I mean here incorrect evaluation of the cooling curve. It can be due to incorrect grain size of the inoculant, because the bigger the grain size, the longer it will take before it's dissolved in the metal. It can be due to an incorrect metal temperature. We have also seen what the effect is if the temperature is different. If we have no wedge test and no thermal analysis, I doubt that you ever can do the optimum inoculation. Sorry to do it like this or to tell it like this. I doubt if you have no wedge test, no thermal analysis, you don't know how much inoculant your metal needs. And you are gambling like in the casino. The second is too early taken tests, because you can do a thermal analysis test, but if you do it and you wait later 10 minutes before you go on, or you wait 20 minutes before you go on, it can be that in the meantime your metal is totally different than at the time you took the test. So pay attention for that. It's very important. Thermal analysis or a wedge test can help a little bit, but better a thermal analysis, and do the test as long as possible and react immediately. Don't wait long time. if you have waited for a long time, you have to do a new thermal analysis test. Yeah, it's you can go on because that's the same what I told you already. Next slide. Incorrect grain size. There are two things. If you have fines, they can fly up when you put them in the metal stream during the tapping. I have seen it so many times. Then the people do it from a fairly high height, and it goes into the metal stream. But the fines of that inoculant flies up, and they appear in the extraction or in the rest of the foundry, but not in the metal. One thing. Too large grains will not dissolve, or can be that they don't dissolve in case the solidification is too quick. Because the bigger the grain size, the longer it takes before they have split. What will it result? It will result in inclusions. You can see it sometimes, inoculant inclusions, or you can see it in inhomogeneous distribution. Then you see an area where there is a lot of nodules, and you see an area a little bit further, and there are very few nodules. So please, the correct grain size is very important. Here you see Castwell has given us an idea from the different sections or grain sizes you can have from the inoculant. They are all usable, but use them properly. So this is, let's say, what we prefer that you should use. You can do something else, but this is by experience one of the good result giving section sizes, grain sizes from the inoculant. There is also mentioned the addition. Please look, there is a range because it can be depending on the need of your metal, that is 0.3, and it can run up to 0.6. Pay attention for the inoculation in the metal in the stream just by pouring. I never go above 0.15, because if you go much higher, you will have an inhomogeneous material and you will get drops. Here you can see if the metal temperature is then also incorrect with a high metal temperature, we lose a lot of fines during the adding of, and high temperature, we have seen it will increase the fading from the first inoculation we have done. If you have a low temperature, the inoculant remains undissolved, and you see a picture there that I many times have seen. That's undissolved, dissolved inoculant. So the risk of inoculant inclusions is there, and an inhomogeneous distribution of silicon is also a very high risk. So please take the correct temperature by experience with combined with the section size, the grain size of your inoculant. Incorrect result. What results you can get that you are not happy with? Well, it's mainly a deviating number of nuclei from the inoculant. Nodularity is very few depending on the inoculation. It's mainly the number of nuclei, the number of nodules who will be, let's say, influenced by the inoculation thing. What can we have? Too low nodule count. We don't like that because we know when we have too low nodule count, we risk that we will have micro shrinkage, and we risk that, let's say, the mechanical properties will be not that good. We risk the presence of carbides. We risk chunky graphite. There can be a too high nodule count, and we can have dross. Now let's go one per one more in detail. Too low nodule count. That means there was too few nuclei at the time of solidifying, which is the result of that there was less inoculation effect at the time of solidifying, that there was less remaining small magnesium sulfur nuclei. This because we know that the magnesium sulfur will fade very quickly, Luckily, we can have barium sulfides, we can have cerium sulfides, but it's a matter also that you have too few sulfides there, and that there is too much fading depending on the time and temperature between the inoculation and the solidifying itself. Too low nodule count, I say again, there is a risk for carbides and microporosity. If we have smaller, let's say, if we have a low sulfur content, because it's a matter of sulfur for getting a good nuclei. You can see it on the graph there, and many times, let's see at the graph, I see people and they always say 0.04 to 0.06 magnesium. You see it at the bottom line is the magnesium content. If you combine that, gentlemen, with 0.006 sulfur and you have 0.04 magnesium, you will risk carbides, a low nodule count, and shrinkage. You can see that. Take the line from the sulfur 0.006, take the line of the vertical line of magnesium 0.04, and you come not in the green area. And the green area is really very important to have as few as possible problems. If you go above left of the green area, the nodularity is too low, and that we see, that's when the magnesium is becoming too low. But pay attention, high magnesium and low sulfur will not deliver sufficient nuclei for having good, let's say, nodule count. There is another one that you can form dross, and dross is magnesium silicon oxide and magnesium 2 silicon oxide 3. They take away as well magnesium as silicon, so they take away nuclei, and taking away nuclei results in a lower nodule count. There is also another one. If the magnesium sulfur is too large in size, you will have less nuclei, and that's the problem of when some of the nodulizing, especially the wire nodulizing, gives in principle bigger magnesium sulfur components who will float up quicker and who will not act as a nuclei, because it must be less than 10 micrometer. If it's more, it will not act as a nuclei anymore. Fading. We all know, I have the formula there of fading of a component in a liquid. It's a general formula, not only for the foundry, but in every liquid when you have something. And you see the difference in density between the metal and the nuclei is very important for it. The size is very important because there's the air, it's the radius, it's, let's say, radius times radius. And the gravity and the viscosity are below the line. Now, the density of the metal is around 7, maybe a little bit less, 6.9 kilogram per cubic decimeter. And how much is now the density of the nuclei? I have put there at the right side. Silicon oxide and magnesium sulfur have the lowest density. So you can be sure that having such a low density, that the speed at which they float up will be very high. I mentioned that also magnesium oxide solid, it's really not coming, it's not practically never appearing in your metal, so we should forget it. But you can see, if you see barium sulfur, 4.25. So compared to the magnesium sulfur, it's nearly the double. Cerium as well with oxides and sulfides, a very high density. It's very good because they will have a very low. Lanthanum sulfur has also 5.66. And that's one of the advantages of lanthanum, that it will not float up that quickly. Not that much compared to the cerium, but it will float up very quickly. So these are very important. We are going to come back on that in the next slide. So the presence of carbides. When do you have carbides? When we have a low nodule count, you can have carbides, especially when the magnesium rare earth relation is very bad, and when we have a low sulfur content. The low sulfur content I showed you two slides before. With low sulfur, less than 0.006, you risk very, very, very well to have carbides unless your magnesium is also very low. If we take the magnesium and rare earths, then we take the lanthanum plus cerium. You can see there, if you add 0.02% rare earths final in your metal, you will always have problems unless you have a very thin casting that solidifies immediately, because the things you have, flotation, exploded graphite, carbides, shrinkage, and all these, they are a process. So they don't happen just at a second. They happen after a certain time. So for very thin castings, you can go a little bit higher without having the problems, but more than 0.02% rare earths, you will have problems. If you take at the left side and you take 0.05 magnesium, you can see it there. That's for heavy castings. If you have with that 0.01 rare earth, make the line. You are definitely in the area where you will have flotation, exploded graphite, and all the things you do. Please make sure that the relation between your magnesium and your final rare earths is correct. And this is a graph I have used all the time. Let's say since around 2000, I use this graph and it gives the best result. So chunky graphite. Chunky graphite is, you see some pictures there. You can have at the left side, that's not, let's say, magnified too much, but you see a few nodules and a lot of chunky graphite. In the middle, you see a restricted area where the chunky graphite is, and a lot of nodules. And at the right side, you see also that there are few nodules, and at the right side, chunky graphite. Chunky graphite is due to too high active cerium. And the thicker the wall is, the more dangerous it is. So please, when you add inoculant with cerium, pay attention that the cerium level before the inoculation is not yet too high, because otherwise you can risk chunky graphite. Let's say chunky graphite up to 30 millimeters wall thickness, it's fairly okay. Above 50 to 75 millimeters wall thickness, it's one of the most frequent results of an incorrect inoculation and nodulizing. Here you see what is the active cerium. Well, the cerium from your spectrometer contains everything. So the active one is the cerium from your spectrometer minus the titanium divided by 5. We have antimonium, lead, and tellurium divided by a half, and bismuth divided by 2. All these elements are compensated by the cerium. That's a very good effect from the cerium, but what's not used for this effect can give later as cerium active chunky graphite. Now, the cerium active, how much should it be? And I give you some examples due to the wall thickness. And you can see there, if you have less than 25 millimeters, you can go eventually up to 0.020%. But if you have more than 250 millimeters wall thickness, you can have only 0.002. And my advice is above 200, no cerium at all. Use a nodulizer, use an inoculant without cerium, because otherwise you will have chunky graphite. So, too high nodule count. I have, by experience, made some lines depending on the wall thickness. From what I know, that gives a good result. The blue line is maybe you don't expect it. It's the maximum, because there is a maximum. If the nodule count is too much, you have graphite flotation. So pay attention for that, not too high, and these are good indications. The red line is the minimum, and the red line, you can see that normally it should always be more than 50 nodules per square millimeter, even in the thickest section. I know customers from the foundries, and I can mention some. You have Siemens, you have General Electric, you have some others. They say the nodule count must be more than 75 nodules per square millimeter. They add it in their order form as an extra rule to make sure that there will be no micro shrinkage and no other problems due to that. But also take a look at the maximum one. There you have, if you have a high nodule count on the right side, it's you can see this is not okay. I can assure you this is a picture taken in India in one of the foundries in the south where they make very big castings up to 20-30 ton in ductile iron. That picture is taken there. Definitely too much, let's say, nodule count. On the left side, you see an interesting graph. You can see when you take the Sharpie V impact test, that's ductility at low temperature. You see that above 20 degrees C up to about, let's say, -10, a ductile iron with a lower nodule count has a better value than the one with a higher. The red one has 310 and the blue one has 180. But if you go further, and that means lower than -25, then the relation reverse. At temperatures lower than -25, a high nodule count has a better result than a low nodule count. That's something for people who make castings who are used at minus temperatures. You see at the right side, dross, it's a little bit, how must I say, a slinger of inclusion that hangs one another. The nodules are concerning nodularity still okay. Nodule count is many times also okay, but not always. And what is it? It's made by the, let's say, the magnesium silicon oxides SiO3 or the magnesium 2 silicon oxide O4. There is a mistake in the text there. It's magnesium 2 SiO4 must it be. It's also made mainly in large castings. Why? Formation of dross needs time. And time before it's solidifying, you only have in large casting. How does it come? Well, it's fairly simple. You see magnesium, and you see silicon, and you see oxygen. So that means if you have a very high active magnesium, who is not bound by sulfur, and a late inoculation, who is providing silicon, you risk to have dross. If you have high turbulence during the mold filling, then you provide a lot of oxygen and you risk dross. So please, for thick castings, look at these figures and make sure that it's difficult to avoid dross, but you will have to take measures to not having it. What other elements are there in an inoculant? We can see cerium, lanthanum, calcium, and so on and so on. They can have a positive as well as a negative effect on the result. And an element, the amount of that element is very, very important. I told you already, calcium is very positive to help magnesium for removing the sulfur. But if it's too much and it's added late, then you will have liquid slag. And liquid slag you cannot keep out of your casting, and you will have a problem. The first effect is the floating speed of the reaction products. And they depend on the density, the size of nuclei, and the temperature of the metal. We have seen the formula there of the speed of floating up. It was the density compared to the density of the metal, and the size, the bigger the size, the quicker it floats up. Which one do we form? This depends on the free energy. The higher in the graphs here, the more frequently they will be there, and the more of them you will have. It depends also on the presence of the other elements. If you have magnesium and you have barium and you add them at the same time, which one will be formed? I don't know. You don't know. It depends on the metal. If you have barium and calcium a lot, which one will be formed? I don't know. It depends on the metal. So it's a matter of what is the amount of elements you have there, which one has the highest free energy. That means the higher here in the curve. It depends also on the existence already from. If you have, let's say, magnesium sulfur from the nodulizing, and later you add barium, it will take time before the barium can take over the magnesium of the sulfur from the magnesium sulfur. So it means time of when you add it is also important. Here is the densities again, and as we said already before, the silicon oxide nuclei is the one who has the highest fading effect because it has the lowest density and will disappear very, very quickly. The same as magnesium sulfur, very low density compared to the others and will fade very, very quickly. So look at this graph when you say, okay, I buy an inoculant with something, you can see here what the effect is. Let's summarize. Again, cerium must be balanced with magnesium. I showed you already many times, let's say, the graph there. It has a low free energy and will form as well oxides as sulfides. So that's doing very, very well. But it's dangerous for initiating chunky graphite in medium and thick wall castings. Why? Because the time to complete solidifying is very long and the reaction can go on. Cerium must also be used when there is presence from titanium, antimonium, lead, tellurium, and bismuth. So pay attention if you start using these elements for one reason or another, and some foundries use antimonium many times or bismuth. With the returns, it come back, and it can be that the amount of these elements increase each time you reuse your returns. So that means then that your cerium must also be adapted to the current level or the actual level at the moment you are going to use it. So cerium should be on top of the other elements, much on the wall thickness, as we said, because it needs time for making chunky graphite, and therefore the cerium can be balanced by antimonium. But without antimonium and the thick section castings, you would definitely will have chunky graphite, mainly under the risers. Why? Under the risers, that's one of the areas where it's the metal solidifies last. Or in thick hotspot sections, you will have it there. Lanthanum is a little bit better than cerium, as we have seen. And some artists mention also that it's a decrease in porosity. But that's in medium and thick wall castings. I have never seen it. And some other authors say in medium and thick wall castings, it has no better effect than cerium. But that's something very personal. Again, here that we said, I put this graph many times there because I find that it's a very, very important graph, and people don't look enough to this. People in your lab who make the chemistry, they should have it with them and look at it. Please pay attention. You get carbides, you get everything who is not okay if your magnesium and rare earths is not balanced. Barium will decrease the fading effect due to the high density, and has also a very low free energy to their formation. So it's a very good element for binding oxides and sulfides and creating nuclei. And it's also less fading than others. Calcium can be used to avoid that you need more magnesium, or will lead to more free magnesium at the end. So that at the end, if the magnesium is too high, you can have exploded free graphite. And what's not put here, but please remember it, it makes liquid slag, which is very difficult to hold even by a filter. Bismuth is also decreasing the fading effect due to the high density, and has also a low free energy, so it's very, very low okay. But it must be compensated by cerium, or will have an influence on the chunky graphite by its relation to the cerium. Pay attention, bismuth is building up in your returns. So it's not because you have measured it now that in 1 week you have the same. It can be much more. Zirconium is mostly used together with manganese, but it will react with aluminium. And aluminium should be restricted due to the initiation of pinholes, especially in the season, the monsoon season, when let's say the humidity in the air is fairly high. Here again, there are 3 times where you inoculant, where the first, the preconditioning, is that an inoculation or not. In some literature, they say it's not an inoculation. In other literature, they say it is. Let's see what it is. Next slide. So the preconditioning is, let's say, a material, a alloy, you put inside the furnace shortly before tapping. Or it can be in the tapping stream towards a nodulizing ladle, it can also be. But I prefer to do it in the furnace. The time is very important because a preconditioner should be dissolved. And that's between 3 to 5 minutes. So if you add one, do it 3 to 5 minutes before you are really tapping. What can it be? A pig iron is a kind of preconditioner. It will increase the quality of your liquid metal. Graphite, but pay attention, because graphite is dissolving very, very, very slowly. So pay attention for that. Silicon carbide, what I told you before. And you have the precast alloy from Castwell. It's containing barium, zirconium, and calcium. That can also be mainly due to the barium used as preconditioner. Silicon carbide, take 5 minutes before tapping. And make sure that you have put it under. Not that it doesn't stay on top of the metal, because then it does not dissolve properly. You have to put it under the metal. Preconditioning improves the quality of your liquid metal before you start any metallurgical treatment like nodulizing and inoculation. Next slide. In the first ladle, we have seen that you can put it together with the nodulizer, and both covered with the steel chips and small tin sized, as you see, sandwich method at the right side figure at the right. You can do it during the tapping itself. You see it in, but I don't like that much, because due to the high temperature and the heat movement, you will lose some of them. So pay attention for that. It is possible. And then the section, the grain size must be somewhat larger during the transfer of the metal, because sometimes foundries do the nodulizing in a big ladle, and then they tap later in small ladles. So it can be that when tapping from the nodulizing ladle in a small ladle, that you have to add some inoculant to make sure that the inoculation is done properly. Pay attention here again, the size is very important, and please use the experience of your people and check to see if everything is okay. Yeah, then we have the other inoculation. You have the wire nodulizing, but many times also it's a double wire system, and you can also inoculate by the same machine with an inoculation wire. It's possible. The stream inoculation, it's something else, and I showed you there two possibilities. You can do it by hand. On the left side, you can see that it's a tube and they put it in the metal. On the right side, you see it in an automatic molding and pouring machine. It's blowing in the stream when it's put in the casting. There is another possibility it's not stream inoculation, but anyhow it is. That is when you use a pouring box, you can add some inoculant over there. You see at the left side it's one, at the right side it's three, a bigger one, a smaller one, and a very small one. This is a system who is independent from the operators, but you need the guidance of supplier from these things, because they must dissolve properly and not at once, not too late. But it's a good system, and for medium-sized casting, it's many times used. And the last one is, of course, the in-mold process, where you can have, as well as a magnesium treatment, you can also have the same system used, not for the magnesium treatment, for an inoculant treatment there. It's done for small castings and a serial production. It's fairly consistent because it's always the same temperature and it's independent from your operator.